So this is a little bit more, I think it's actually out of section 2.1. Tonight's assignment is going to be partly out of section 2.1 and partly out of section 2.2. We'll do that sometimes just to give you some additional practice, and in this case, something a little bit more. So we have something that's called the sandwich theorem. In some textbooks, it's also called, in other textbooks, the squeeze theorem. Same thing. So what it says is if we have a function f of x that is always less than, greater than or equal to g of x, but less than or equal to h of x, for all x not equal to c, because, again, we're going to be doing a limit, and we don't care what happens at c. Okay, that's why we don't have to have that in there. In some interval about c, and additionally, we find that as x goes to c, g of x and h of x both go to the same thing, then f of x must also go to that same value. So basically what we've got here is I'm going to draw a simple picture. You don't need to draw it if you don't want to, but if like this is h of x and this is g of x, sound effects are optional, and f of x is somewhere in here, then right here where the top one and the bottom one go to the same value, at that point f of x has got to go to the same value as well. Right? It gets squeezed or sandwiched in between those two. In all honesty, we don't make a lot of this at this point. We're going to come back to this idea way later in the second semester, almost at the very end. Okay? But we can make some use of it to help us figure out certain limits. For example, if I want the limit as x goes to 0 of x squared times sine of 1 over x, and we want to show that that's equal to 0, it's not immediately obvious what's going to happen here. However, what we can look at is like, okay, sine of anything is always between what and what? It's always between 1 and -1. So what we can say is that x squared times -1 is always going to be less than or equal to x squared times sine of 1 over x, which is always going to be less than or equal to x squared times 1. All right, everybody's good with that reasoning? And so what I'm going to do is find, well, what is the limit as x goes to 0 of x squared times -1? Well, that's going to go to 0. And the limit as x goes to 0 of x squared times 1 is also 0. Those two things are equal to one another. And the function that we have in mind is in between the two. So therefore, do you guys ever use the 3 dots for therefore? I got a yes and 2 no's. I think that gets taught internationally way better than it does here. I think we don't, somehow or another, um, in America, we've stopped using set notation and things like that. There's a whole bunch of little um, symbols that you can use. You know, there's this one's for therefore, but there's also such that, and there's all these different things. This implies that we just don't use much. So therefore, the limit as x goes to 0 of x squared times sine of 1 over x has to also be 0.
I have a question.
Yeah.
How do you know that the first two go to 0?
Oh, as x gets close to 0, what does x squared get close to?
0?
And if I multiply it times -1, it's still 0. Yeah. No, it's okay. It's okay. The graph of these is, I think, really kind of interesting. Oh, I must have closed it. So if I've got the graph of negative x squared, because that's what that first one is going to be, right? And the other one is just positive x squared. And then I look at x squared times sine of 1 over x. And, let's do a zoom standard and see what that looks like. So the graph of x squared times sine of 1 over x, let's zoom in. Maybe we can see this a little bit better. So there's negative x squared. There's positive x squared. And what this does is it gets trapped in between these two. Another interesting one, if I change this to just sine of x, it doesn't really change what's happening, although it's a cooler graph if I remember correctly. Oh, I was completely wrong. I'm thinking of something else apparently. But you see how it still gets trapped in between those two. All right. So the sandwich theorem also applies for limits as x goes to plus or minus infinity. So for this, we have kind of hand-waved on this when we've done this. We go, well, sine is, it's always finite, and it's over something really big, so it's going to go to 0. We can be more formal with a demonstration of why this works. So we know that -1 over x is always going to be less than or equal to sine of x over x is always less than or equal to 1 over x. Then if we do the limit as x goes to infinity of negative 1 over x, that's 0. And that's equal to the limit as x goes to an infinity of 1 over x, which is likewise 0. So this means then that therefore, by the sandwich theorem or the squeeze theorem, whichever one you want to call it, the limit as x goes to infinity of sine of x over x is also equal to 0. Part of the reason we also do this is to get you used to the idea of justifying your answers. Okay? So here I'm applying the theorem, and the theorem says that the function in question has to be in between these two on some interval, and that the limit as x goes to whatever we're interested in goes to the same thing, then the limit of the function we're interested in goes to that same value. So although I haven't named the sandwich theorem, I could say then by the squeeze theorem, but I have laid out all of the things that were requirements. We have this requirement, we show that we have met that requirement. And then we show that this is true, and then therefore we can say this is true. So that process of, if there are requirements, we have to show that we have met those requirements, and therefore we can make this conclusion. Okay? That's going to come up a lot. Okay, any questions about that? All right, so a bit more time.